Channel Programming with Pirai. In this video, we are going to solve a Leetcode question number 231 power of 2. Given an integer n, return true if it is a power of 2, otherwise return false. And it is integer n is a power of 2 if there exists an integer x such that n is equal to 2 power x. If we can make or we can represent an integer in format of 2 power some value, it is called as power of 2, right? So if you already seen my basic bit manipulation video, there I have discussed this problem, right? Once again I am discussing this problem here. See here, n is equal to 1, then I can represent 2 power 0 is equal to 1, right? So it is true. 16, so 2 power 4 is equal to 16. Fine. And sometimes some people misunderstand this problem, like if even numbers occurs, then there is a power of 2. But it's not the case. If there is 6, take for example 6. If there is 6 cannot be represented by 2 power something value, right? We cannot represent 2 power something value in 6. So there the test cases will be failed. So how can we approach this problem? Let us see the approach. First let me take number 16. Let me take the number 16. 1 0 0 0 0. It is my binary equivalent for 16, right? Now first thing that comes into my mind is to check the constraint. Let me check the constraint. It is what? 2 power 31. It goes up to what? 2 power 31. So can I make what is 2 power 0? It is 1. 2 power 1, it is 2. 2 power 2, it is 4, 8, 16, 32, etc. so on. And then I want to check whether this 1 is equal to this 16, whether this 2 is equal to this 16, whether this 4 is equal to 16, whether this 8 is equal to 16, whether this 16 is equal to 16. Yes, true. Then return true. This is my first approach coming to my mind. Yes. So what is the time complexity for this approach? The time complexity for this approach is we are going from what? 0 to 31. So overall it is O of 32. It is approximately equal to constant time. But still this doing this operation will take a larger amount of time, right? Doing this operation will take larger amount of time because whenever we are using power of function, it takes about log n times, right? So it takes about log n times, and space comes it doesn't take any space. So this is my first approach. So talking about the second approach, whether I can think in reverse order, like take the 16 and divide by 2. What is my answer? It is 8 and remainder is 0. Take 8 and divide by 2. Again 4 0. Take this 4, divide by 2. 2 0, then 1 0. Fine. Now I got an answer 1. Before that there is no remainder except 0. So I can say like take for example 2 is represented 1 0 and 4 is represented 1 0 0 and 8 is represented 1 0 0 0. 16 is represented 1 0 0 0 0 and 32 represented 1 0 0 0 0. Like that, only one ones will be occurred in every power of 2. So I can count how many set bits, the number of set bits in a number is equal to 1. Then I can say it is a power of 2. Right. So if you don't know about the set bits, then you can see my video on counting bits. In that I can use 3 approaches. One is a basic approach, another one is Brain's approach, that is Brain's algorithm approach. Then another one is a DP approach. We don't need this DP in this problem. We do in these 2 approaches. Fine. Okay, talking about time complexity. What is the time complexity? As we know, the time complexity is O of log n, right? O of log n, time complexity, and space complexity is O of 1. Fine. So this is the second approach. Now what is the third approach? Can we optimize it? Yes, we can check it. First we want to write from 0 to something, some value, up to 10 or up to 8. So 0 is can be written as 0 0 0 0 and 1 is written as 0 0 0 1. 2 is written as 0 0 1 0. 3 is written as 0 0 1 1, right? Now 4 0 1 0 0. 5 is 0 1 0 1. 6 is 0 1 1 0. 7 is 0 0 1 1 1, right? And 8 is what? 1 0 0 0. Observe carefully, observe carefully. Take this 2, take this 2, take this 2. This 1 occurs here and this 1 occurs here. Take this only, this 2 bits, this 2 bits, 2 bits. 1 occurs here and 0 occurs here. 1 occurs here and 0 occurs here. Okay, okay. Let me take another observation. Take this 3 bits and take this 3 bits. The first bit is 0 here and first bit is 1 here. And this second and third bit here is 0 and second and third bit is 1. Yes, yes. Now take this all 4 bits. Take this all 4 bits. First bit in 7 is 0 and first bit in 8 is 1. And last 3 bits in 8 is 0 and last 3 bits in 7 is 1. So I can say wherever 0 occurs, 1 occurs in the n plus 1, in the n minus 1. That is, if I take 8, wherever 0 occur in 8, 1 occur in 7, and wherever 1 occur in 8, 0 occur in 7, right? So I can say if I do AND operation, the value will be equal to 0, right? The value of these two things will be 0 because 1 0 0 0 0 1 1 1. So it will be 0 0 0 0, right? Right? So I can say if a number n and its number minus 1 is equal to 0, then I can say it is a power of 2. It is a power of 2. Simple. Clear? So this is my third approach. So what is the time complexity and space complexity? Time complexity will be O of 1. Space complexity will be O of 1. See here, these both are what? Constant. So it is so efficient, right? It is so efficient. Now let us see up to this. Let us see up to this 3 approaches. Then we can see further approaches, right? First, let me explain this 3 approaches. See here, this is the first approach. I want to take each and every bits, each and every power of 2 up to 31. Then I want to check whether it is equal to the given value. If it is equal to given value, I will return true. Else I will return the false, right? So let me run this. Here using this will be expensive, right? It is not an efficient way, right? So it is running successfully. Let me comment it. Then we can go to the next. Here I'm using the basic approach. I am not using the brains algorithm. See here, result is equal to 0 if 0 is less than or equal to n is less than or equal to 0, then I will return false. While n result plus is equal to n ampersand 1. So I am taking the LSB bit 1 by 1 and adding to the result. If there is only one set bit, my result will be what? 1, right? So that's what I am returning, right? And I am right shifting n 1 by 1 in each and every iteration. So let me run this. Yes, it is running fine. Now this can be also done in recursive, but it's not optimal way. Just understand what is in the recursive manner. See here, check of n. If n is less than or equal to 0, return false, right? If n is equal to 1, return true. If my n by if 2 by 2 is equal to 0, equal to 1, right? If I reach that position, I will return true. See here, I have wrote here, right? See this example. I have wrote 1 by 1 and at last my quotient become 1, right? At that point I will need to stop and I can declare as it is true. So that's why I use here. And In front of that, if there occurs any false condition, like if there occurs any remainder as 1, because see here, all remainder are 0, right? All remainder are 0, right? If any of the number that gives a remainder 1, I will return false, right? So that's why I have used return n mod 2 is equal to 0. And if the condition only satisfied, I will call the recursive call for n by 2. Fine. This is my logic for recursion call. Let me submit it. And talking about time complexity and space complexity, both time complexity and space complexity will be O of log n, because log n for time complexity is based on the recursion. It runs up to log n times, but still it creates a recursion stack. That's space complexity of log n, right? So this is my bit manipulation approach, right? So return n is greater than 0 if the n is greater than 0, and also n and n minus 1 is equal to 0. That is 8 and 7 is equal to 0, right? So it is a 2 power, this is a power of 2, right? So let me submit it. Right, fine. Now we can also use a inbuilt function. This is a last approach. This is a fourth approach. In this inbuilt function, we can use a log 2 and log 2. We want to take a log 2 for n, and we want to take a log 2 for n. If taking this log 2 don't give me a fraction or decimal point, then it can be my answer. Yes, let us take for example, let us take 2, 4, 8, 16. What is the log 2 value for 2? It is 1. What is the log 2 value for 4? Just I write here log 4. Log 4 can be written as log 2 power 2. So 2 log 2 base 2. So it becomes what? 1. So 2 into 1, it becomes 2, right? So it is 2. Then it is what? 3. Then it is 4. See here, these all are whole numbers, right? These all are whole numbers. But still, if we take 5, it will be around 2 point something value, right? So that's why we are just coming to the conclusion, like if it returns a whole value, then I can say it is a power of 2, right? If it is 2 point something or any point value, it is not a power of 2. That's why I'm going to take a seal and floor of a value. If I take seal and floor of the value 4, I will get 4 only for floor and 4 only for seal. So it is equal, right? It is equal. But if take for example 4.5, what is the floor value? Floor value will be 4. And seal value will be 5. So it is not equal, right? So I can return false. This is my fourth and last approach. Let me submit it. It is an inbuilt function approach, right? So don't prefer this approach. We want to prefer this bit manipulation approach, right? It is submitted successfully. Thank you.